Hi, welcome to Algebra 2 Common Core. Today in lesson number 6, we're going to take a look at how all of those transformations that we've been working with in this unit can help us to solve some real-world problems, which of course is a focus in Algebra 2. So in exercise number 1, I've got a projectile has a height given by the function h of t is equal to negative 4.9 times t minus 4 squared plus 153. T is the time measured in seconds, h is the height measured in meters. Now what we'd like to do is take this function and describe it using the transformations on the parent function y equals t squared. Don't be concerned that we've changed our variable from a normal x squared to now a t squared so that we can know that t stands for time. We want to then take that set of transformations and figure out what our maximum height of the function is and at what time it must reach that maximum height. So looking at my function, h of t is equal to negative 4.9 times t minus 4 squared plus 153. Remember that when we are trying to list down the transformations in order, we always want to start on the inside and work out. Very similar to doing order of operations. So I look inside the parentheses and I say t minus 4. That's going to be my horizontal variable. So if 4 is being subtracted from the horizontal variable, that tells me that my first step is going to be to shift my function 4 to the right. Next, I'm going to take a look at the coefficient of t minus 4 squared, and I see that that's 4.9. So when I'm multiplying my variable times 4.9, that means that I've got a transformation that's a vertical stretch. And again, make sure you're always telling which direction and how much. So this is a vertical stretch of 4.9. The negative in front of the 4.9, when I'm negating the horizontal, that tells me that I'm actually going to do a reflection. Normally we would say a reflection over the x-axis, but remember that we've replaced x with t, so I'm going to say a reflection over the t-axis. And the last part of my transformation that I can see in my function is that we're adding 153. Since that's happening outside of the variable t, I know that that's happening in the vertical direction, so that tells me that I've got a vertical shift. Since it's a positive value, I'm going to say we are going to vertically shift the whole function up 153. So what I'd like to do is then apply these 4 transformations to my normal vertex or turning point of the function t squared. So if I had the function y equals t squared to begin with, then I know that the vertex of this function, because it's my regular parent function of the parabola, is just 0, 0. So I want to take that vertex 0, 0, and I want to apply all of these transformations. So I'm just going to label them by which number transformation I'm doing. So when I take 0, 0 and I do transformation number 1, I'm going to shift it to the right by 4. So that changes my first variable to 4. I'm adding 4 to the first variable. So I get the new vertex 4, 0. In transformation number 2, when I do a vertical stretch, I take the y coordinate and I multiply it by that vertical stretch number. So I'm multiplying the y coordinate by 4.9. But since the y coordinate is just 0, my vertex is going to stay at the point 4, 0. When I apply transformation number 3, that's my reflection over the t-axis. Remember that that just negates my y value. So I take the negative of the y but the y is still 0, so I'm going to still have the vertex 4, 0. All I've done there is actually turned my parabola upside down. So now instead of 4, 0 being the minimum of an up parabola, it's going to be the maximum of a down parabola. Finish off with transformation number 4, which says that we're going to vertically shift up 153. So that's going to take my y coordinate and add on 153. So here's where my vertex changes to the point 4, 153. Now, what does this mean? The 4 is my t coordinate, so t equals 4 seconds is how long it's going to take for the projectile to get to its maximum height. The h of t coordinate is equal to 153. That represents meters, and that's going to be the maximum height of the projectile. Now, of course, we could check this on our graphing calculator by just putting this function into y1, of course, replacing the t with an x on our calculator. We'd have to adjust our window to make sure that we could see a maximum of 4, 153. So the most important thing would be to make sure that my y max goes above 153 in order to see this vertex point. So you can see how using transformations has helped us to kind of dissect this function that I was given and see what has happened to my easy parabola y equals t squared with a vertex of 0, 0 to get the actual maximum point of this function. So this was another way of finding the vertex. In the last chapter, remember how we did vertex form? We were actually given vertex form right here, so we could have also read the vertex right from this vertex form. So the vertex form would have also told us that 4, 153 was going to be my vertex on this projectile. For problem number 2, you're going to need your graphing calculator, so if you don't have it with you, please pause the video and go get your graphing calculator. Now I'm going to start by solving this problem using my calculator. So I've posted some of the screenshots from my calculator. Let's start with my y equals menu. So in y equals, what I'd like you to do is put this first equation, the one that I'm given. Let's go back and look at the problem. An arch is to be constructed so that its shape follows the curve y equals -1/2 x squared plus 10x. X measures the horizontal distance along the ground, and y measures the vertical height of the arch above the ground. Both of these are measured in feet. So it says to draw a sketch of the arch, use your calculator to determine the height of the arch at the turning point. So it's nice and easy to enter this into my calculator. So in y1 I put -0.5 x squared plus 10x. We'll get to what's in y2 in a few minutes. Now, I thought that it might be a good idea to take a look at this function and say, okay, what would be a good way to count in my x-axis? So along the x-axis on my graph and in my table, it worked out nicely to count by 2's. So I set up my table of values where my table set was 0 and my delta table was 2 so that it would count by 2's. Now as you can see, I'm getting a nice parabola shape. I can see that in my table because there's symmetry with the first and the last value at 0, and the middle value, of course, is 10, 50. So I can see right there the vertex of my parabola just by looking at that table of values. Remember, if you want kind of to ballpark where you're going to be for that vertex, we can always use the equation x equals -b/2a. So in this equation we could have said -10 divided by 2 times -1/2. So that's giving me an answer of 10 for my x-coordinate of the vertex. In general, if you double that value, I can get what my biggest x value should be for my graph. Again, you're going to have to adjust your window on your calculator. So on my calculator, when I hit the window key, I made my x max be equal to 20, and I made my y max be equal to 160. And, oh, I'm sorry, I made it just 60, not 160. And as you can see, on the y-axis, I counted by 5s. On the x-axis, I counted by 2s. And in both cases, I started with mins of 0. So we can see on our graph that I've got that maximum point right there identified at 10, 50. Now go ahead and take a few minutes to draw that on your grid, matching your axis. So I went along and counted by 2s to get to 10, and then by 2s to get to 20. And then going up my y-axis, you can either count by 10s to get to 50, and reproduce this graph using the table of values. In your notes, please put the table of values and please graph this. So pause the video while you do that. So we've examined this function graphically using our graphing calculator, but I'd like to also take a look at it algebraically. So before I can describe the transformations that are going on with this function, I'm going to have to convert this equation that's given to me in standard form. I want to convert it over to vertex form. So let's remember the steps that we did in the last unit, because this is going to be really important for any parabola, to be able to take a parabola in standard form and convert it over to vertex form. So remember that for vertex form, we're going to start, if there's a constant being added on the end, then we'll move that constant over to the y side. In this case, I don't have a constant, so there's nothing to move. My next step is to factor out a coefficient of x squared, because I really can only complete the square if I've got a 1 in front of the x squared. So in this case, what I'm going to do is factor the negative 1/2 out of both terms that are on the right. So it's easy when I've got the x squared term. I just put the negative 1/2 in front of parentheses. Now be careful here. With the 10x, I'm going to factor out a negative 1/2. That's really the same thing as saying 10 divided by negative 1/2. Well, 10 divided by negative 1/2 means I can divide by multiplying by the reciprocal. So that would be 10 times negative 2, which of course gives me a negative 20. So when I've factored out a negative 1/2, I'm getting a negative 20x inside my parentheses. Now we're going to complete the square, so we need to leave a spot in order to get the constant that goes in that trinomial. Remember to take half of the center term, so half of negative 20 is negative 10. When I square negative 10, I get 100, so I'm going to add 100 in that spot right there. But I haven't really added 100 to the right side. Remember that it's being multiplied by negative 1/2, so I've really added to my right side negative 1/2 times 100, which is negative 50. So on the left side of the equation, I also have to add negative 50. So right now I have y minus 50 on the left side. I have a negative 1/2 in front of my trinomial, but I'm ready to factor that trinomial, so that's going to give me x minus 10 squared. As my last step, remember that we're going to take the 50 on the left side and move it over to the right side by adding 50. So I'm going to have negative 1/2 times x minus 10 squared plus 50. This is, of course, the vertex form of the parabola. And yes, once again, I could read off the vertex right from that vertex form. So I can see that the vertex is 10, 50. So I'm going to jot that down and say 10, 50 is my vertex. Let's once again talk about the transformations. So for the transformations, my first step, and again now I'm looking at this vertex form equation. My first step is going to be to shift to the right 10 units. My second step is going to be that vertical stretch because I see that I've got to multiply by 1/2. Technically it's not going to be a stretch, it's going to be a compression, but I'm doing a vertical stretch of 1/2, multiplying any y coordinate by 1/2. Because of the minus in front of that, that's going to be a reflection over the x-axis. And my last step is going to be a vertical shift. That vertical shift this time is going to be that plus 50, so that means I'm going up 50. So let's take our normal parabola vertex, 0, 0, and let's apply these 4 transformations. Transformation number 1 says shift to the right 10, so that's going to give me the point 10, 0. Transformation number 2 says that I'm going to do a vertical stretch of 1/2, so I multiply my y coordinate by 1/2, but it stays at 10, 0. For transformation number 3, I'm going to reflect over the x-axis, so that maintains the point 10, 0. And for transformation number 4, we're going to shift up 50 units, so my new vertex is going to be at the point 10, 50. So we've seen at least 3 different ways in this one example of coming up with the maximum point on that function, 10, 50. We did it graphically, then we did it using our vertex form just by examining the equation and identifying the vertex, and we also did the transformations to our original vertex of 0, 0 to get a vertex of 10, 50. Now there's one more part of this question, so I'm going to go back up to the top here and look at that last part of the question. This now says if a second arch was to be created that had the same height but only half the width, determine an equation for this arch. Now what we notice is that to keep this same height, I'm not going to make any change in my y direction, no vertical changes. Instead, I'm going to change it by half the width. Remember that half the width means that what we're going to do is do a horizontal, I'm going to write it up here because I'm out of room, but horizontal compression of 2. So what that means is I want to find the function value at 2x. Remember when we're doing horizontal compressions, we always have to take the reciprocal. If I'm doing a horizontal compression of 2, I'm really taking half the width. So half the width means use 2x in my function. So let's go ahead and find that new function value. So my equation used to be y equals negative 1/2 times x. So I'm going to replace the x with a 2x and then square it. Plus 10 times 2x. I'm going to algebraically find this equation, so it's a negative 1/2 times 2x squared gives me 4x squared. 10 times 2x gives me 20x. So my new equation is going to be y is equal to negative 2x squared plus 20x. Now go ahead and type that new equation into your graphing calculator and check on the calculator that I do in fact get a parabola that only has a width of 10 instead of 20, but it still has the same height of 50. So this is an important skill to be able to do. Looking at our last example, number 3, we're given a function g of x, and we know that g of x is an odd function that is 1 to 1. We're given a point, g of 7 is equal to negative 2. And what we want to do is figure out what point must lie on the inverse function g to the negative 1 of x, and then explain how we made our choice. Now we know that we are starting with the point g of 7 is equal to negative 2. So what that means is that the point 7, -2 is on our graph. But because we have an odd function, that tells me that the point, remember that odd means opposite inputs produce opposite outputs. That means that the point -7, +2 will also be on the graph of G. So here's the information that I have about G. Now, since my function is 1-to-1, that means that I can take the inverse of it. So let's talk about what information I have about the inverse function. If G of 7 is equal to -2, the inverse means that I can take the output and convert it to input and vice versa. So G inverse of -2 would equal +7. That means that the point -2, 7 would be on my inverse graph. But because it's an odd function, opposite inputs give me opposite outputs. I could take the opposite of the x and the opposite of the y and get another point that's also on the inverse. So when I'm looking at the choices, I can look for either this one or this one to be an answer for my inverse function. So looking back on the choices, I see that the one that I'm going to pick is this point right here. So my explanation is that my inverse function G of x, G inverse of x, and G of x are both odd and 1-to-1. So therefore I know what I wrote down up here, that opposite inputs produce opposite outputs. So that's going to give me that point that I found right there. Have a great night, and we'll continue to practice with all of these transformations. I hope you saw the value of all these transformations in these real-world application problems, because it just gives us another tool in our toolbox that we can use when we're taking a look at functions and being able to tell what's going on within the function. We'll see you tomorrow. Bye-bye.